Hi, everyone. So today it is my pleasure to welcome Professor Stephen Lowe from Caltech, who will be presenting OPF Hardness and ACN. Perhaps Stephen's biggest accomplishment to date is surviving the Berkeley EECS PhD program. He received his PhD in EECS from Berkeley in 1992 and was advised by Professor Praveen Varaya. His thesis title was Traffic Management of ATM Networks, Service Provisioning, Routing, and Traffic Shaping. Perhaps you still remember that, although it's many years ago now. I was thinking it would be, it's almost the 30-year anniversary of your graduation, so perhaps we could host you in person for a 30-year reunion of sorts. It would be our pleasure if that's a trip you'd be willing to make.
That would be lovely. Thank you so much, Keith.
Yeah,
that's right. So ATM is not an automatic teller machine. It used to be a network, I guess, in the late 80s and early 90s that was expected to take over the world from desktops to the core network. But within a span of maybe 2-3 years or so, it's completely collapsed and taken over by IP network. And yeah, in the mid 90s or so. So, and the rest is history.
Well, fascinating. A little bit of perspective, and we'll see which aspects of our dissertations will be completely taken over in the years shortly following. But needless to say, Professor Lowe made a number of contributions in fields including communication networks and power systems. His communication systems contributions include applying dual algorithms to internet congestion. And his power systems contributions include power flow convexification with applications to both transmission and distribution networks, and a number of other areas, including feedback optimization, demand response, distributed frequency regulation, and recently EV charging with the adaptive charging network at Caltech. So that's the ACN. And we are delighted to welcome him back to Berkeley virtually and hope to host him in person soon.
Thank you very much, Keith, and thank you all for the organizer. So I'll talk about two topics, and let me explain the acronym. Oops, does that work? Yes, okay. So the three Ps, the first piece is just introduction. Some of you probably already know, but I just want to formulate very quickly what is optimal power flow problem, which is OPF, and its semi-definite relaxation. And then the two pieces are one is about the hardness of OPF problems. Is hard in theory, but in practice, it seems to be easy in some sense. And we're trying to understand on the theory side, why that is the case. And the third is about electric vehicle adaptive charging network that you hear more about. So let me first acknowledge the people whose result that I will present in this talk. The first part, OPF hardness, and it's done by my current PhD student, Fengyi Zhou, and also a visitor student, Yu Chen. She just started as an assistant professor at Chinese University in Hong Kong. And the EV part, charging network, I will present results from Zach Lee, who just recently graduated a PhD from Caltech and joined the PowerFlex, a Caltech startup, which is part of the EDF now. And Sunesh Sharma, who's in the audience, doing PhD at Berkeley, and also Tongxin Li, a grad student at Caltech. And also the work is really built on working very closely with a Caltech startup PowerFlex systems. Zach and probably Sunesh as well work very closely with the founders and also the engineering team of PowerFlex, but also built on the work before they joined by founders at PowerFlex. Okay, so I guess we don't need convincing why we care about smart grids and also EVs. 84% of total greenhouse gases in the US are related to energy use. And of this, the electricity generation and transportation consume about 2/3 of all energies and emit between 55 to 60% of all greenhouse gases in the US. And therefore, to decarbonize or drastically reduce greenhouse gases, we need to electrify transportation and we need to generate electricity from clean, renewable sources. So here's the model. So a model we can think of, a power system model, you can think of as represented by a graph where there's a set of nodes, which the buses, and a set of lines. And every line is characterized by 3 numbers. So these are complex numbers. The first one, YJKS, is the series admittance, is a complex scalar. And the other 2, YJKM and YKJM, are the charging admittances associated with this line at each end of the line. So in general, these 2 YJKM and YKJM may not be the same. It depends on what the graph models. If the underlying physical system includes transformers, for example, then in general, these 2 shunt admittances can be different. And at each node, there are 3 variables. We'll focus on 2 of them. One is this small sj or si, that is a real and reactive injection, power injections from node I to the rest of the network. And the second is the voltage phasor at node j. I and j should be the same. And then there's a third, which is the current injection we'll see later on. And therefore, you can think either you have a network that can be represented by a graph associated with each node, or nodal variables, the injection Sj, the voltage phasor Vj, and then also the current injection at each node. So there are 3 variables associated with each node, and then there are 3 parameters associated with each line. For those who are familiar with power system models, then you can also think of this model or these 3 numbers as a pi equivalent circuit of a line. So you have a series admittance and you have 2 shunt admittances. If you are interested in how the current phasor, the vector I over the network, how that depends on the voltages in the network, that relationship is linear through a admittance matrix. But if you're interested in how the power injection, the S, which is a vector of SJs, relate to the voltage phasor over the network, that relationship is nonlinear. That's a power flow equations. It can take different forms, and here's one of them. So this is how the power injection Sj relates to the voltage phasors on its neighbors. And this is simply power band, so Kirchhoff laws and Ohm's law. It's nonlinear. There's a quadratic, it's quadratic in this complex voltage phasor. And OPF is simply a constraint optimization. And the reason it is important is it underlies numerous power system applications. It takes the form where you want to minimize a certain cost, C as the function of the injection vector and the voltage phasor, subject to 2 kinds of constraints. There's an equality constraint, F equals 0, and inequality constraint, G less or equal to 0. Depending on the application you're looking at, the cost function may be different. The equality constraints and the inequality constraints can be different. Even the variables can also be different, but typically you can always reduce them back to the power injection and the voltage phasors. And in fact, later on, we're going to replace that, eliminate S and look at the optimization problem as a function of the voltage phasor only. So the cost functions for some could represent generation cost, power loss, and so on. The equality constraint typically will contain power flow equations, which is these nonlinear equations we saw before, or is approximation like DC power flow. Inequality constraints typically are some kind of operational constraints. It would include, for example, injection limits, voltage limits, line limits, and other constraints depending on your applications. So in more detail, it looks something like this. So this is a power flow equation, which will be part of your equality constraint, which is quadratic equation. Operational constraints can look something like this, the injection constraint, which can be the generator capacity limits, for example, the voltage magnitude constraint, and also the line limits. So if we look at these constraints and typically objective functions as well, they are quadratic, and therefore you can always write for OPF of this form, write them as a quadratic constraint, quadratic program, where the cost, let's say the field cost, is a function, quadratic function of the voltage phasor. So there is a cost matrix C0, which is typically positive semi-definite. So the objective function typically is nice, it's convex. But the cost constraints, so this set of matrices are Hermitian, but not positive semi-definite. And therefore, the feasible set is non-convex. And that's where a lot of computational challenges arise. And here's a picture of that from Ian Hiskin. You have very simple network, three nodes, 3-bus network. And if you project some of the, say in this case, generation from generator 1 and 2, then the feasible set looks something like this. It's pretty beautiful or pretty challenging. It's non-convex. So, and therefore, this quadratic program, QCQP, is a non-convex QCQP. And one way to think about relaxation is to write each of this, which is a scalar here, write it as a trace of a matrix. In fact, a product of two matrices, the matrix of the cost matrix and also a RAM1 matrix, which is VVH. VH, by the way, is a Hermitian transpose. So you take the transpose and then you take the complex conjugate. And therefore, V here is a column vector. VH is a row vector. So this is a scalar. But you can write such a quadratic form as a trace of the product of these two matrices. One, again, is the cost matrix. One is this RAM1 matrix, VVH. And therefore, everywhere you see the variable V, it appears as VVH, and you can think of, you have a problem that optimizes over matrices. So this is, you live it to the matrix space. So you replace VVH by W, then you get this equivalent problem. The interesting feature of this problem is that while the original problem is quadratic in V, so nonlinear in the variable V, it is linear in the matrix variable W. This is not for all matrices, but matrices that are positive semi-definite, which is a convex constraint, and RAM1, which is a non-convex constraint. And therefore, if you write it in this form, then all the computational complexity arises because of this non-convex RAM1 constraint. If you solve a problem where you ignore this non-convex constraint, you get a semi-definite relaxation. So you get a convex problem over the matrices. So that's the standard SDP relaxation for a QCQP, non-convex QCQP. And this is this kind of problems that we study. So pictorially, what you do is that, so here is an example where the feasible set is this black curve, and therefore it's non-convex. When you do SDP relaxation, you enlarge the feasible set to the purple region, which is a convex set that contains the black curve. You can do even simpler relaxations, what's called second order cone relaxation, through which you would enlarge the feasible set to the yellow region that contains the purple region. So if you blow up the picture, what you see is that the Pareto front, so this front, assuming the cost is going in this direction, decreasing in the lower left direction, then the optimal point is going to lie on this face. So what happened here is that the boundary of the convex purple region is exactly the black curve. And therefore, when you minimize over the convex purple region, solving the relaxation, the optimal point will happen to fall on the black curve, which is feasible and therefore optimal for the original non-convex problem. So in this case, you have exact relaxation. So solving the relaxation will produce a globally optimal solution, even though in general, it may not. And in fact, if you do SOCP relaxation, so what happened in this case, if you blow up the figure, the yellow region strictly contains the black curve. And therefore, if you minimize over the yellow region, you will get a optimal point that does not lie on the black curve and therefore is infeasible for the original OPF problem. But it provides a lower bound in cost. Okay, so that's the relaxation. So that's the background. Let's go to the second part, the core part, which is OPF hardness. Let me summarize what I'm going to talk about in the second part, which is that, so we saw OPF is non-convex. Not all non-convex problems are NP hard, but OPF is both non-convex and NP hard. And in practice, however, it seems to be easy in the sense that if you solve semidefinite relaxations, very often you get global solutions. Or if you run local algorithms, say gradient descent, Newton-Raphson, you will often get globally optimal solutions. There's no guarantee, but that's what we observe empirically. So we try to understand what are some of the underlying analytical properties of this problem that may help explain these two phenomena. So we'll look at exact relaxation. We'll present a recent result on exact relaxation, and then we look at some conditions, both sufficient or necessary conditions for these two phenomena to happen simultaneously. That is the relaxation will both be exact and there are no spurious local optima. So these are, let me go to the details of this. So OPF is indeed an NP-hard problem, and here's a recent proof by Pascal Van Henrich's group. So they look at the simple case where you have a radial network, so the single phase tree topology, there's a single demand on the network, and you fix the voltage magnitude, and therefore the voltage variable becomes just the phase, and then the injections, real and reactive power. And they ask whether there exists a feasible solution for this problem. Well, they can reduce the NP-hard subset sum problem to this AC feasibility on the tree network, and therefore proving OPF in general is NP-hard. So the subset sum network is given a set of integers and a number. The question is whether there exists a subset of the integers that will sum to that number. So, and therefore we know OPF is hard in theory. Empirically, it seems to be easy. So here's some really early results, almost 10 years ago, when we worked closely with Southern California Edison and also for IEEE, where we looked at a bunch of attribute test systems. These are radial networks and including some SE networks. If you run second order cone problem, you get exact results. You get exact relaxation and therefore globally optimal solutions. For a mesh network, SOCP is not exact typically, but if you run SDP, you get exact result. You get exact global optimum. Okay. Even in cases where you don't get exact relaxation, if you use the solution of your relaxation as an initial point and just run gradient algorithm, a sequential quadratic algorithm actually in this case, then you can typically get to a point that is very close to the lower bound provided by your inexact relaxation. So it's certainly bounds an upper bound, perhaps a non-straight upper bound for your globally optimal solution. So within say 0.5% of optimality gap. So it's very close. And therefore, potentially it's due to numerical issues. The point is that if you just run local algorithm, you are likely to get globally optimal solutions or very, very small optimality gap. So this is the old result. The recently there is a paper from Los Alamos National Lab where they look at a very large set of OPF test cases. If you run semidefinite relaxations, very, very often you get exact solution. Right? There are cases highlighted in bold that don't get exact solutions. And if you do some enhancements, say tightening the bounds, adding valid cards, then it will close most of the remaining optimality gaps. And therefore, again, it shows that indeed you could get non-global solutions if you run local algorithm, or you run exact semidefinite relaxations, but very often you get global solutions. So let's try to understand maybe at least some of the analytical structure that help explain this. It doesn't completely explain this empirical experience, but at least help justify some of the empirical experiences. One is exact relaxation. So there's been quite a bit of work in the last decade or so on conditions for exact relaxation on radial networks. Mesh network is much harder. So I'll present one by Fengyu Zhou, the Caltech PhD student, and Yu Chen, a research student that appeared in CDC 2019 on multi-phase radial network. So let me get to that. Right, so this is a CDC paper. Okay, so we care about radial network because almost all distribution networks have tree topology and are radial networks. And a lot of the innovations in smart grid appear in distribution systems. And therefore, the physical system, indeed, you have a tree structure. Every bus or every node has, let's assume, 3 phases. In general, you could have single phase, 2 phases, or 3 phases. The result extends to that, but the notation is just more cumbersome. So let's assume it's 3 phases everywhere, so the notation is simpler. Then you have this physical network that's in tree structure. But if you look at the Kirchhoff law, the electromagnetic interactions between phases will couple the variables in different phases. So for example, if you look at the current on these lines in phase A, phase B, and phase C, they depend on the voltage drop, not only in phase A, but also in phases B and C. And therefore, as far as the Kirchhoff law is concerned, the variables are all coupled. But because of the macro tree structure, you can write down the Y matrix, admittance matrix, for a single phase equivalent circuit, where every bus in the single phase equivalent is identified by both the bus number and also the phase. So every node in a single equivalent circuit will be bus 1A, 1B, 1C, for example. And so in this example, 3-bus 3-phase network, YI3, Y13 is a 3x3 matrix, admittance matrix, series admittance matrix. And in the admittance matrix, then you see this macro structure where Y13 is connected, and therefore the off-diagonal entry 13 is this minus Y13 matrix. And the diagonal entry is simply the sum or the negative of the sum of the off-diagonal entries in the row. Similarly, for example, bus 3 is connected to 1 and 2, and therefore in 1,3, there is minus Y13 matrix, and in position 3, 2, there's a minus Y23, and then the diagonal matrix is their sum, negative of their sum. And therefore, you can think of the 3-phase radial network in terms of the single phase equivalent. And you can therefore apply all your models and analysis and relaxations to the single phase equivalent. As a result, a unbalanced multi-phase OPF is still a QC-QP. It takes this form where the only, so everything's linear, except that the positive semi-definite constraint is convex and the RAN constraint is non-convex. Ignore the RAN constraint, you get the SDP relaxation. So we say the relaxation is exact if you get a solution that is of rank 1. Then you get exact relaxation. That's the definition. Then finally prove a sufficient condition for this problem that is 3-phase unbalanced, but over a radial network. For this OPF problem, he proved a sufficient result for exact relaxation. So the result is like this. For each bus J, we call it a critical cost bus if it contributes positively or non-zero contribution to the cost, overall cost. So the cost can take this form. For example, is a weighted sum of the real power injection and reactive power injection. So if this generation cost, real power, then CJIM phi is 0, for example. So bus J is a critical bus cost bus if CJ phi is non-zero for some phi. So as long as it contributes non-zero, it has a non-trivial contribution in this sum, then J is a critical bus, cost bus. It is a critical constraint bus if you look at the bounds on the injections on both the real power injection and reactive power injection. If at least one of the bounds, one of the 4 bounds is finite, then it's a critical constraint bus. Okay? Then they show that the relaxation is exact if no critical buses are adjacent and no bus is both a critical cost bus and critical constraint bus. Now, the constraint bus condition seems to be quite restrictive. It's less restrictive, it's still a bit restrictive, but less restrictive than it appears. What really is needed is that if you solve the relaxation at the optimal injection, if the optimal injection lies strictly within the feasible set or within its bounds, then it is not a critical bus. And therefore, critical bus really only depends on if the optimal injection attains one of its 4 bounds. Then it's the critical bus, then it cannot be adjacent to another critical bus, for example. So that's the sufficient condition. So there are known results on when semidefinite relaxations will be exact. The other phenomenon that we observe is that if you run local algorithms, typically you get global solutions. So this is widely observed empirically, but as far as we know, there's no analytical support why this is the case. So Fengyu proved last year, CDC, is sufficient condition for both phenomenon to happen, both that the relaxation is exact and there's no spurious local optima. So let me explain his result. So you consider a very general case where you just have a non-convex optimization where the cost function f is continuous but convex. So the cost function is nice, but subject to a constraint where the feasible set is non-convex but compact. Okay? And then relaxation is simply you enlarge the feasible set to a x hat, which is convex. That's relaxation. So it's very general. It can be semi-definite relaxation. It can be some other convex relaxations. As long as the feasible set is convex and contains the original non-convex feasible set, then that's a relaxation, right? So here's the picture. You want to minimize this nice cost over x, which is non-convex, but you do the relaxation over x hat, okay? So let me know if it's too noisy. It's kind of noisy. I can close the doors and windows.
I think it's okay. I'm not having trouble with the background.
Okay, great. So, so we say the relaxation is exact if you solve the second problem and get a solution that is optimal, feasible, and therefore optimal for the first problem. Then we say the relaxation is exact. This is a very general formulation. And his key result is a Lyapunov-like condition for both the relaxation is exact and any local optimum is globally optimal. So let me explain his result in more detail. So the first concept is that a path, so given any infeasible point, so a point x that is not in the set x, but is in the set x hat, right? So it's given any infeasible point, there's a path, which is simply a continuous function, h indexed by x from 0 to 1, and it brings this point from the infeasible point x to some feasible point inside the capital X. So that's a path, which is simply a continuous function of that that does this, right? So then he showed is to show that the relaxation is exact, even only if for every infeasible point X, there is such a path to bring it back to inside the feasible set, such that the cost f of this h of x of t, which is simply the location when you go from the infeasible point X to a point that is feasible. So the cost f is non-increasing, and at the end, the point that is feasible will have strictly lower cost than the original cost. So that's the condition on the path. If for every infeasible point, there is such a path that brings you back to the feasible point, which has a strictly lower cost, then the relaxation will be exact and is necessary and sufficient. So that's the first concept about path. And the second concept, he defined a Lyapunov-like function like a MATLAB logo, where Vx is 0 if x is feasible, and strictly positive if it is infeasible, but inside the x hat, okay? So that's the Lyapunov-like function. compare with traditional Lyapunov function, for those who might be familiar, then the traditional setting, we have a dynamical system, y dot equals f of y, that specifies implicitly a trajectory, right? Given an initial point, this dynamical system, y dot equals f, will specify how the system will evolve. And we are interested in conditions that will guarantee the trajectory, yt, will converge to an equilibrium point, y star. And that will be the case if, for example, there is a Lyapunov function v of y, such that vy is really positive if y is not at the equilibrium point, and it's a 0 if it is. And along the trajectory determined by your dynamical system, y dot equals f, the Lyapunov function strictly decreases along that trajectory. So that's the classical Lyapunov stability, that if you can find such a Lyapunov function, then the dynamical system will be stable in this sense. In comparison to what Feng's problem, we don't have a dynamical system, so we don't have a ODE, for example, that specifies the trajectory, and the dynamical system is replaced by an optimization problem. So a trajectory is a path that Feng defined that brings a infeasible point X back to the feasibility. And the goal is not to drive the system, there's no system, this optimization problem. The goal is not to converge to any particular point, but we want to go into the feasible set X. And a Lyapunov-like function that Feng defined has the same property, the first property is the same, where v of y is really 0 as positive if y is not, or it should be if y is not in the set. Otherwise, it's 0 if y in the set. So cut and paste error. And the second condition will be a condition in his theorem, which is similar to the condition here, essentially that the Lyapunov function will be non-increasing, so decreasing along that trajectory or the path that you have to figure out. And then there's another condition that he defined in his Lyapunov-like function definition, which is not only we need the Lyapunov function to be, say, decreasing along the trajectory, but the cost of our optimization problem also need to be decreasing along the trajectory, along the path that you have to find, and in fact strictly decreasing at the endpoint. Okay? So that's the comparison between the two. So here's his result. The condition is such that for every infeasible point X, there is a path and also a Lyapunov-like function such that two conditions are satisfied. One is that both the cost function F and the Lyapunov function V are non-increasing along the path as T goes from 0 to 1, X goes from, or the location goes from the infeasible point X to a point that is feasible, right? So both functions are non-increasing along the trajectory, and at the end, the cost is strictly lower, right? The thing we saw before. The second condition is sort of a regularity condition. So the set of paths, one for every single infeasible point, is uniformly bounded and uniformly equicontinuous. So it's uniform both along 0, 1 trajectory, but also across all infeasible point X. So it's quite a regularity condition. All right, so it looks something like this. As you go from X to inside the feasible set, both the Lyapunov function V and the cost is decreasing, roughly, that's the condition. So Feng showed that these two conditions are necessary. If your problem has the property that all local optima are globally optimal and the relaxation is exact, then these two conditions must be satisfied. They are not sufficient. And the issue is that if you look at the set of local optimum, so a local optimum can be globally optimal, which is the point we are after. It can be what you call genuine local optimal, which is like this point A and D, or it can be something like point C, which is what we call pseudo local optimal. Condition C1, C2 eliminate the genuine local optimal A and D, but not this kind of local pseudo local optimal C. For that, you need a third condition, which roughly says that the cost function along the trajectory not only has to be non-increasing, it needs to be decreasing fast enough. That's what the third condition says. If you have that condition, then indeed, you eliminate this kind of a pseudo local optimal. And he shows that these three conditions are sufficient for the problem to have no local spurious local optima and for the relaxation to be exact. So this is a very general setup that applies to OPF, applies to low rank SCPs and so on. So let me, okay, so I need to speed up a little bit. So this is just a picture where his condition characterizes the intersection where problems have both properties. Okay? So for those who—
And Stephen, just interject, you don't have to rush through on our account. This is great. So go whatever rate is appropriate for you.
Oh, okay. Okay. Okay, so let me comment a little bit on this then. So you could potentially have problems where at the complement, which means that for this problem instances, the non-convex problem is exact. But if you run local algorithm, you may not get global solutions. So that's in the complement. Similarly, on the other end, that you could have problems where you run local algorithm, you get global solution, but if you run exact relaxation, it may not be exact. So what is interesting in OPF is that it seems to possess both properties. And Feng's result basically characterizes this intersection. It's not an exact condition yet because there's still a bit of a gap between necessary and sufficient condition, but they seems to be, hard to say, seems to be on the surface pretty close. Right? C1, C2 are necessary, C1, C2, C3 are sufficient. Okay, so for those who might be a bit familiar with the really nice disflow model for distribution systems proposed from Berkeley in 1989, before my time. Where if you can formulate OPF using this model for distribution systems is a really, really nice model. It has lots of interesting and useful properties. Then your OPF will have convex constraints, in fact, linear constraints, except for this quadratic constraint, which is nonlinear. If you change the equality to inequality, then you get a second order cone. And that's a second order cone relaxation for your original non-convex problem. So Feng can apply his result to this problem, and indeed, you can construct a Lyapunov function for this problem, which looks something like this. And indeed, you can construct explicitly for every infeasible set, infeasible point X, this path H of X. It's a little bit noisy outside. Let me know if I need to do anything.
I think it's still okay, actually. I don't know. Yeah, Gabriel's not having trouble either. If anyone is having trouble, put in the chat.
It's probably bad for him, but not for us.
Yeah.
Okay, great.
Yeah, other audience members have said that it's okay as well, Stephen. So whatever works for you.
Okay, thanks. Great. Okay, so for this problem, when you construct explicitly the Lyapunov function V, and also the set of paths, one for every infeasible set. And indeed, he checked that they satisfy C1, C2, and C3. And therefore, if there's no lower bound for Sj, then this SOCP relaxation is guaranteed to be exact. But moreover, if you just run any local algorithm, you will get a global solution. So this no spurious local optimal result seems to be new. And this is just two bus example, what V looks like, what the HX looks like, and so on. So let me skip that detail. Okay, so again, this is a summary that OPF seems to be hard in theory, but seems to be easy in practice in the sense that semi-definite relaxation seems to be very often exact. If you run local algorithms, you typically will get global solutions. And there's some analytical properties that help sort of justify what we observe doesn't completely explain, but helps. Okay, let me get to the last part, which is this electric vehicle adaptive charging network, and talk about the results by Zach Lee, Sunash Sharma in the audience, and also Tongsin Lee, a PhD student at Caltech. So many people contributed towards this work. Building this infrastructure is a lot, and there's some of the early contributors, especially people, the founding team at PowerFlash and some of the early visitors at Caltech and many others. All right, so let me go to, so I will basically show you pictures. That's all I have. To show you the infrastructure, that the first testbed that we built at Caltech, and eventually there's a Caltech startup that commercialized it. So let me show you some of the pictures. And then the ACN research portal, which is a research facility that we built on top of the physical infrastructure that we hope will be useful for the research community. So everything is open source, and we really love if anyone not only will be interested in using them, that would be great, but also contributing towards that, especially if you want to lead this project and so on, that's fantastic. So Zach has graduated, he's still supporting this and that, and Sunas now is at Berkeley, so maybe he'll be interested in leading this project if this is useful for your PhD research. So let me tell you about all this. Okay, so we know that California has made a commitment to have 100% clean electricity by 2045. Pretty ambitious. While New York is 2040. So there are more than a dozen states in the US now that really commit to 100% clean electricity or energy in around mid-century. And also 5 million EVs or zero emission vehicles by 2030. So for calibration, California has about 15 million cars. There are lots of nice things why we want to electrify transportation, and here's one of them. You probably know of the duck curve problem. If you look at the duck curve today, so this is April, and if you want to just fill the valley, that can support 13 million EVs. So it huge potential for workplace charging. Also, there's some survey that seems to suggest that if workplace charging is available, drivers are twice as likely to actually get an EV. All right, so here's a physical system that we built, the first system that we built back in 2016. It consists of, so it's one of the California Caltech garages, this California garage. So we built two transformers with panels and conduits and chargers and all of that. And that's the physical system, smart charger. So it's capable of real-time communication, computation, and also actuation. There's a cyber system to go with it, where as the driver plug in the car, there's a mobile app. The driver can tell the system how much energy I need. So I need 30 miles. When do I expect to depart? Say 5 p.m., for example. So given this information, the system in the cloud will jointly optimize the charging schedule of EVs in the garage. You can optimize, for example, the electricity charge, depending on time of use, depending on demand charge even, for example, or you can optimize to charge EVs as fast as possible, for example. So the point is that you can optimize the charging in a way so that all drivers will get their energy demand before their deadline, while optimizing whatever objective you want to optimize, say optimizing the use of renewable energy, for example, and subject to the safety constraints, the capacity limits of the transformers, of the lines, and of the chargers are respected. So the way we do this is that every 2 minutes or so, we form a QCQP. So this is a convex QCQP, quadratic constraint quadratic program. You solve that QCQP, the solution will tell you how to charge every EV in the garage for the next 2 minutes, and then you repeat the cycle. So it's a model predictive control. So this is the first test bed that we built at Caltech Garage back in 2016. He has 54 adaptive programmable chargers that George, who was the founder of PowerFlex, a former student from Caltech, so that's him, working with his brother in the garage at night on the 18th of 2016, building the chargers and everything. And so this charger was not commercial. He actually built it himself with all the smarts and everything. 2 transformers and breakers and all of that. Okay, so this is 2020. By March 2021, ACN includes a total of 200 level 2 chargers and 6 DC fast chargers spread across Caltech, JPL, and also a Caltech LIGO research facility and an office building in Northern California. And this is just one site. And I believe this is a Caltech garage, the second Caltech garage. This is DC fast charger. So we started commercial operation. It started as a test bed and things break. Everyone charged for free. We support the electricity using research grants, everything. And then around at the end of 2018, it transitioned to commercial operation taken over by Caltech facilities. And we lose sort of the ability to play with the test bed as we wish. And therefore, the idea is that we want to build a layer, software layer, on top of the physical infrastructure that will allow researchers to do research on top of this ACN research portal. It consists of 3 pieces. There's ACN data, which will be charging data that we collect. So I get into more detail, and then clean it, anonymize it, put it on the web so that people can use the data for any research purpose they want. And a simulator, which is open source, that simulates the charging facility, and you can use it for many purposes. I'll go into a bit more detail later on. And then hopefully an ACN live testbed that will allow users to apply the algorithm to cars in Caltech Garage. So I'll let you know what the status is on that one. So the Caltech Garage started operation in 2016 as a test bed. By July 2020, it has delivered 1 gigawatt hour of electricity corresponding to 3 million miles and 1,000 tons of avoided CO2. There's some of the early commercial deployments. The company is acquired by EDF, which is one of the largest utility company in the world based in France. Now they have close to 10,000 chargers now around the country, but mostly in California. So there's some pictures. So this is a current, which is a charging rate as a function of time. There are different colors. Each color represents 1 car, and you stack them up. Then you can see that the charging is adaptive. And in fact, the objective function in this case, I think back in 2018, is still mostly you try to charge as fast as possible, but there are some regularity terms in the objective functions and so on. And the reason is because the cost is flat. There's no TOU. Otherwise, you see maybe a different pattern. But the point is that you could optimize and really use a much lower infrastructure, smaller infrastructure, and less costly infrastructure to satisfy users' demand. So at Caltech, for example, each driver typically on average stay for 6 hours, and they could finish charging in 2 hours. So there's a lot of flexibility. Okay, so oops. So this is a NREL deployment where over the weekend you can see this duck curve, right? So there's a very steady building load, and then the net demand minus the PV generation, you can see this nice duck curve. During the weekday, the building loads fluctuates a lot more, but you can still see a duck curve. And here you can add the EV load on top of that in a way that minimizes or mitigates demand charge. So in this case, it's very simple. You can cap. Oh, so I should stop soon. So this is the, if you control the EV charging smartly, then you can mitigate the demand charge. This is the COVID. So this is around March 2020. In fact, we can look at the drop. So this is number of sessions in blue and energy delivered daily in orange. So this is when we started to charge payment, calculate a commercial operation, that you see a drop, and then this is COVID. But now it's sort of starting to get back up. And if you look at, say, the user behavior, for example, the arrival, the distribution is actually different. After COVID, for example, the arrival time seems to have a significantly larger variance, right? So probably means people have more flexible hours. So that's the physical facility, and we want to build this ACN research portal consisting of ACN data, simulator, and also ACN live. So let me just say a bit more on each of the three. ACN data, right now, this is October 2020, there are 53,000 EV charging sessions. So those, each session consists not just the arrival, departure times and energy delivered, but also detailed charging process, the current is a function of time on 5 to 10 second resolution. So they are publicly available, growing on a weekly basis. I think it's now updated every week. Sunas may probably know more accurately than I do. And they can be used for example, modeling user behavior, evaluate your charging algorithm or charging facilities. Or if you think of your multiple such smart garages on a feeder, what is the impact on the feeder? So, or you can use it for training your, or evaluating your learning algorithms, for example. So there's some picture to show, let's say, the flexibility at Caltech during weekday, during weekend, at JPLs, and so on. So you can look at how much flexibility is there, for example, and how that flexibility translates into the savings in the capital cost. Right? So this is the data from Caltech, from JPL, compared with optimized scheduling, comparing the optimized scheduling with uncontrolled charging, then you save more than 3.5 times network capacity, and that translates to capital investment. But it also translates to operating costs if the garage faces demand charge. So some interesting user behavior, their duration, how much they stay, and the energy delivered. And you see this very nice line that corresponds to level 2. And there's some DC fast chargers. And it also tells you the average duration people stay in the garage. So it's 7 hours now, used to be 6 hours. And then average energy is used to be about 10 kilowatt hour. So this data includes newer data back in 2016, 17 or so. So both numbers seems to be higher now. And also you can look at the fine-grained charging data, right? So this 10-second, 5 to 10 second time resolution, and try to say, can I build a more realistic battery model, for example? And that's an interesting learning problem because even though we have very detailed charging current data, we don't know the SOC. And therefore you have to deduce for example, the battery behavior from the tail. Now, how do you extract the tail? And then how do you cluster them? And the reason we want to cluster them is the belief that even though we have a large number of charging curves, they really are generated by a small number of drivers and using a small number of models, battery models. And therefore, the expectation is that this large number of charging curves will be classified nicely into a very small number of sort of representative battery behaviors. So that's a very interesting learning problem. It involves some new learning ideas because of how do you extract the tail and then how do you do the clustering. There's a feedback between these two processes. You have to iterate them and so on and so forth. So there's some interesting, perhaps learning applications of the data. Okay, ACN Sim. So Sunas and Zach and working with the PowerFlex engineering team built a very nice simulator that simulates, say, the charging network, the chargers, the EVs, the batteries and constraints and so on. So this is a very realistic simulation model for the physical system. It is coupled with ACN data that drives the simulation, for example. You can also include other signals, for example, utility tariffs, solar generation, or even real-time LMPs, for example, that goes into the simulator that drives the simulation. It has an interface that allows you to, if you're interested in trying out your charging algorithm, you can do your algorithm, conform to the interface, then you don't have to worry about anything inside. Then your algorithm can generate charging commands, give to the simulator will execute and give you back the measurement, the next state, and then your algorithm can continue. So it has been used for various purposes, for example, evaluating, if you want to optimize, minimize the RAM requirement for the duck curve problem, right? And then depending on how many garages you have, what is the optimal charging schedule and what is the impact on the RAM requirement, for example. So you can use that to do that. The ACN Live, the idea is that the interface will remain the same. Instead of a simulator underneath the interface, there's the actual Caltech garage, the testbed or the real system. And your algorithm, after you've tested on the simulator, it is nice and safe and everything, then you can run it on the real system. That's the ACN Live testbed. There will be a module that will intercept your command, check that it is safe. If not, then they can do the default command and give it to the car. Otherwise, you will pass your command to the actual car, get the measurements, send it back to you, and then your algorithm can continue. So the idea is that if the interface remains the same, the algorithm doesn't even need to know whether it is a simulator underlying that or the real system. So there's a delay in the ACN Live because we need to work with the PowerFlex, the company, to have the real system that actually works on this thing. So this is not complete, but there's a lot of groundwork that has been done. And everything's open source, extensible. Anyone interested in doing that, that would be fantastic. Please do let me know. I think I will end here. So you can find more information at this website. Thank you very much. I will stop here.
Wonderful. Thank you so much. That was a great talk, Stephen. So I'm going to turn off the recording and then we'll have a question and answer session.
Thank you.